Good morning, everyone. Good morning, ma'am. I am Marian Chari Dondo. My report is all about linear programming minimization by set-list method. A minimization problem, it deals with the cost, but the slack variable do not contribute any cost. Rather, the artificial variable, it contribute the biggest of the cost. So I have here a problem, so we try to solve this one. So first problem is a livestock breeder needs at least 6 units per day of nutrient A and at least 3 units of nutrient B for her calf. And that the breeder can choose between two different feeds, feed 1 and feed 2. Each bottle of feed 1 costs $3 and provides 1 unit of nutrient A and 2 units of nutrient B. Each bottle of feed 2 costs $2 and provide 3 units of nutrient A and 1 unit of nutrient B. How many bottles of each type of feed should be bought to minimize the daily cost? So in this problem, we need to see first our variables. So our variable here are the cost. So let y1 the first feed, then y2 is the second feed. Then we are now we have now our variable, so we minimize the cost. So minimize cost. So our cost here is $3. In first feed, we have a $3 cost. So we need 3y1 plus the second cost is $2. So 2y2. Now we have a cost here. So first we need to identify the constraints. So in this cost 3y1, we have a first constraint here is the cost of $3 provides 1 unit of nutrient A. So y1 because we have a 1 unit of nutrient A plus and $2 we need to provide 3 units of nutrient A. So 3, 1, 2. So the problem here, we need to at least 6 units per day of nutrient A. So it is said it is greater than 6. We have now our first constraint. Next, we need to find the second constraint. The second constraint here is if the $3 provides 2 units of nutrient B, so we have 2y1 plus the second constraint, the cost of $2 provides a 1 unit of nutrient B. So y2 is greater than, we need a 3 units of nutrient B for her calf. So 3. Now we have our second constraints. So we don't have any non-negativity constraints. So we put y1 is greater than equal to 0 and y2 is greater than equal to 0. So now we're done with this minimization method. So we need to transpose it into a matrix so that we can have a maximized function. So now we have a minimized equation here. So we have to put it in a matrix table. So we put this of 1 plus 3, 1, 3, and 6. Then 2, y2 is 1, then 3. So this equation 3, 2, 0. So if we need to transpose this so that we can get a dual problem. In this column, we need to put here 1, 3, 6, 10, 2, 1, 3, 3, 2, 0. So after we get this matrix, we cannot transpose it into maximize problem. So maximize to 6 x plus 3 x1 x2 this is the maximization based in our matrix now. And then we need to find our first constraint based on this matrix. So our first constraint here is this one. So we have now our minimization, maximization equation. So we need to transpose that matrix into first. In the first constraint here, we have a x1 plus there 2x2. So in order to transpose this minimization into maximization, we're going to transfer also the symbol. So it is now less than equal to 3. Then the second row, we get 3x2, 3x1 plus x2 is greater than equal to 2. So we have now our second constraint. So it is also a non-negativity constraint. So we put x1 is greater than equal to greater than equal to 0 and x2 is greater than equal to 0. We can get our, now we can have our maximized cost. So we have to transfer it in equation. So 6x1 plus 3x there. So x1 we get there is 1, 2, and 3. So 1x1 plus 2 there, 2x2 is less than equal to 3. So the sign here, because we're already in a maximization problem, so we need to change also the sign. So from greater than equal to, we are now in less than equal to 3. So next, the second column here, 3, 1, 2. So 3x1 plus x2 is less than equal to 2. So we don't have any non-negativity constraint. So x1 is greater than equal to 0 and x2 is greater than equal to 0. Now we have to form our simplest table. So this one x1, x2, s1, s2 equal, then its ratio. So 1, x1 is 1, 2, x2 is 1. S1 we don't have we have a slack variable here 1 because this is the first constraint. So 1, we don't have S2 because we don't have a slack variable 2, then 0, then 0, then 3. This one is the ratio 3. This one 3 is x1 is 3, this one 3, x2 is 1, so x1 is 1. S1 zeros because this is the second constraint, so we don't have a slack variable 1. Instead, we have a slack variable 2 because this is the second constraint, so we add here plus 1. So 1, then is equal to 0, then the ratio is 2. This one is 2. Then, the maximized cost, it is negative 6 here. X1 is negative 6, then negative 3. Then, we don't want to have the slack variable 1 and 2, so 0, 0. Then, this is the third equation, so we put here 1, then 0. We have here a simplex table. Now, we can find here the least negative. So, the least negative here is negative 6. Negative 6 into ratio 3. So, our pivot here is 3. So, 3. Transform here in a simplex table. So, 1/3, our root 2 is greater than root 2. 1, it becomes 0. 5/3, our slack variable is 1. Slack variable 2 is negative 1/3. Then 0, the ratio is 7/3. So when negative 1, row 2 is 1, plus row 1 is greater than row 1. So we get 1, x1 1, x2 1/3. Slack variable is 0 because we don't have S1 here. Then S2 is 1/3, then 0. The ratio, it gives a ratio of 2/3. So 6R2 plus R row 3 is greater than R3. So 0, negative 1, 0, 2, 1, 4. So 7/3 into 5/3, it gets 7. If then 2/3 into 1/3, we get 2. So we have now our new pivot, this 5/3, because if we said we get that is negative. So now later, so our new pivot here is 5/3. So if we transfer the 3/5 in row 1 is greater than row 1. So it gives a x1 is 0, x2 is 1, slack variable is 3/5, slack variable 2 is negative 1/5 is equal to 0, and the ratio is 7/5. So a negative 1/3 in row 1 and root plus row 2 is greater than row 2. It gives a 1, 0, negative 1/5, S2 is 2/5, then is equal to 0, and the ratio is 1/5. So it gives this 0, 0, 3/5, 9/5, 1, and 7/5. So these are now our optimal solution because we cannot see here a negative sign. So the answer to that problem is the livestock breeder will obtain minimum daily cost if she uses 3/5 bottle of feed 1 and 9/5 bottle of feed 2 for a daily cost of 27/5. So it cost of $5.40. Let's proceed to example number 2. So this is a minimization problem. So the cost here is 2x1 minus 3x2 plus x3. This is the objective function. Then 3x1 minus x2 plus 2x3 is less than or equal to 7. This is the first constraint. The 2x1 plus 4x2 is greater than negative 12 is our second constraint. Negative 4x1 plus 3x2 plus 8x3 is less than or equal to 10 is our third constraint. And this one, x1, x2, and x3 is a non-negativity constraint. So we try to solve this one. We need to convert this negative 12 into positive. So 3x1 minus x2 plus 2x3 is greater than or equal to 7. Then 2x1 plus 4x2 plus this symbol is converted into less than equal to because the negative here it becomes positive. So it becomes the same sign. So this 12. Then negative 4x1 plus 3x2 plus 8x3. So they are now in the same symbol. Now we can solve it. Now we have a same symbol here. Then we need to convert this symbol into equal to. So in standard form, we need to add a slack variable in order to get an equal sign to this equation. So this one is 3x1 minus x2 plus 2x3. So in order to get this equal sign, we need to add a slack variable. Plus x1 is equal to 7. Same the second solution, so we need to add a second slack variable. The negative 4x 1 plus 3x 2 plus 8x 3 plus s3 is equal to 10. So this is now our standard form. Now we have our standard form, so we can now minimize our loss. So our loss here is z is equals to 2x1 minus 3x2 plus 6x3. So we need to add our slack variable here. Plus the slack variable is 1, so we add the 0s1 plus 0s2 plus 0s3. We have the example cost here, so we need to write a syntax table here. So first thing we do is we need to put the basic variable here. So the our basic variable is this one, x1, x2, x3, s1, s1, s2. So we put here x1, x2, x3, s1, s2, and s3. So we have here our basic variable, then we write the CG, which means the coefficients of these variables. The coefficients of x1 is 2. x1, 2. Right here, 2. Then x2. The x2, the coefficient of x2 here is negative 3. So negative 3, then 6. Our s1 is 0. s2 is 0. And s3 is 0. So this is the solution. Iteration. So after that, we need to put our slack variable here. Our slack variable is S1, S1, S3. So we put S1 here is 2 and S3. So the value of our slack variable are all 0. So we put the same line 0, 0, 0, 0, 0. Now we're already done with this table. So we put all the values of our constraints here. So our S1, the first constraint here is this one. This is the first constraint. So we fill up the standard form here into a syntax table. So 3, negative 1. Our x2 here is negative 1. So it's negative 1 and 2. Our S1 is 1. Then we don't have n slack variable 2 and 3. So we put 0 here and 0. Then the second here, then fill up this table. So our x1 is 2, then 4. Then we don't have x3, so 0. So we don't have also slack variable 1, so 0. Then this 2, we have the slack variable 2, so we put here S2 is 1 and 0. Then the third, this one is negative 4, then 3, 8. S1 is 0, S2 is 0, and S3 is 1. So we already fill up all the tables. So we just need to find the solution and the ratio. So how to get the ratio here? So we need to find the key element and the key column so that we can solve the ratio. So after that, we need to find the ZG. So in order to find the value here, we need to multiply the 0 by 3, then 0 by 2, 0, each element we multiply 1 by 1. So 0 by 3 is 0. I think all numbers multiplied by 0 is 0. So we get 0 over here. Then we can now find the CG and GJ. CJ minus CG, this is the formula to find here. So CG here is 2 minus 2. So 2 by minus is 2. So we just need to copy this one because these numbers are all negative 3, 6, 0, 0, 0. Now the solution here is just copy this one. 7, 12, and 10. So when we get the ratio, we need to get the k. So the set is the least positive. So this column are equal. And the least positive is 3. So we need to multiply this. So if we get this ratio, we need to 7 by 3, then 12 by 4, 10 by 3. So we get this 7 by 3 is 7. 12 divided negative 4, so it's negative 3. Then 10 divided 3 is equals to 3.33. So we can now get our least positive. So this is negative. So we have a less positive. So 3.33 are less positive. So we cannot get the optimal solution yet because there is a negative here. So we need to do another thing. We need to draw another table so that we can attempt it all positive so that we can have our optimal. Now I'm done with my examples. By the way, a minimization of simplex problem, it was created by George Stevens of Stanford University. So that's all for today. Thank you so much.